In ancient Greece, during the 5th century BCE, Democritus was one of the most important philosophers who sought to understand the structure of matter. According to Democritus, the atom was the smallest fundamental particle that constituted matter. He explained this concept with a simple example: take an apple and cut it in half, then cut those halves in half again, and continue this process of cutting. According to Democritus, if you keep dividing the halves, eventually you will reach a point where you obtain a piece so small that you can no longer divide it. But not because your knife can't cut it, but because this particle is truly indivisible. This particle was what he called the atom. John Dalton was an English chemist and physicist who developed the modern atomic theory in 1803. Dalton proposed that all matter is composed of small, indivisible particles called atoms. According to him, the atoms of each element are unique, and all atoms of the same element have the same mass and properties. The atoms of different elements, however, have different masses and properties. Dalton also argued that chemical reactions occur through the rearrangement of these atoms and that atoms are not destroyed in the process. His theory revolutionized the understanding of matter by providing a scientific foundation for earlier philosophical ideas, significantly advancing the field of chemistry. Dalton's work was supported by experimental evidence that confirmed the existence of atoms and laid the groundwork for the modern understanding of chemistry used today. J. Thomson was an English physicist who discovered electrons in 1897, a breakthrough that revolutionized our understanding of atomic structure. Through his experiments with cathode rays, Thomson found that atoms were composed of smaller particles and that these particles carried a negative charge. He named these particles electrons. Believing that the atom was neutral overall, Thomson proposed that these negatively charged electrons were distributed within a positively charged substance. This idea became known as the plum pudding model, where the electrons were thought to be scattered like raisins in a pudding. Thomson's discovery of electrons revealed that the atom was divisible and had a complex structure, marking a significant step forward in the development of modern atomic theory. Ernest Rutherford was a physicist from New Zealand who made a groundbreaking discovery about the structure of the atom with his gold foil experiment in 1911. In this experiment, Rutherford examined how alpha particles were scattered through a thin sheet of gold, revealing that most of the atom is empty space, but there is a dense, positively charged nucleus at the center. This nucleus accounted for most of the atom's mass, while negatively charged electrons orbited around it. Rutherford's nuclear model of the atom completely transformed previous models of atomic structure and laid the foundation for modern atomic theory. In 1913, when Niels Bohr developed his atomic model, he made a fundamental change in our understanding of atomic structure. Bohr's atomic model proposed that electrons orbit the nucleus in specific energy levels, with these levels corresponding to discrete energy packets. This model was a significant advancement in explaining atomic spectra, as it showed that electrons could only transition between certain energy levels, leading to specific lines in the light spectrum. Bohr's model revolutionized our understanding of atomic stability in energy levels, and is considered one of the cornerstones of quantum mechanics. In 1926, Erwin Schrödinger made a significant advancement in understanding atomic behavior with his wave mechanics model. In Schrödinger's model, electrons were considered not as particles but as probability waves located within specific regions. This approach suggested that electrons were not in fixed orbits but existed within a probability cloud formed by a wave function. This model provided mathematical equations to explain atomic energy levels and electron behavior more accurately, laying the foundation for quantum mechanics. Schrödinger's wave mechanics revolutionized our understanding of subatomic particle behavior, helping us grasp the complexity of the physical world more comprehensively. James Chadwick revolutionized atomic physics with the discovery of the neutron in 1932. By identifying neutrons within the atomic nucleus, Chadwick demonstrated that, alongside protons, neutrons were present and had a mass very close to that of protons. This discovery illuminated previously unclear aspects of the atomic nucleus and revealed that protons and neutrons constitute the majority of an atom's mass. Chadwick's discovery of the neutron significantly contributed to nuclear fission and nuclear energy research, becoming one of the cornerstones of modern nuclear physics. Quantum mechanics is a theory that revolutionized the understanding of atomic and molecular behavior, forming the foundation of modern atomic theory. This theory addresses the behavior of atoms and molecules through probability waves and quantum states, which cannot be explained by classical physics alone. Quantum mechanics proposes that electrons do not occupy fixed orbits but rather form probability clouds through a wave function. It also introduces fundamental principles such as particles exhibiting both wave and particle properties simultaneously, offering new perspectives on atomic structure and chemical bonding. This approach provides a more accurate explanation of atomic energy levels, chemical reactions, and matter interactions, laying the groundwork for modern physics and chemistry.